in the previous lecture we discussed improper integral. So let us directly go to the definition. So improper integral is defined in this way, that is integration from a to infinity f of t dt is defined to be the limit of x tends to infinity integral a to x ft dt, where a is some real number. A is
सर पिछली क्लास ओवर नहीं होगी?
yes. So I'm just revising bit the definitions which I will be using it again.
Okay, sir.
So this is the definition of the improper integral which we use, and this such an integral is known as the integral of first kind, right? So this way we find the improper integral of given function, and one of the important example we discuss is 1 upon t power p, where p is some real number. So we discussed that this integration 1 to infinity 1 upon t power p dt converges if p is greater than 1, and it diverges if p is less than or equal to 1. So we shall be using all these results in this lecture also. And we know that whenever we have a series n equal to 1 to infinity an, this converges if and only if n from any other number to infinity an is also converges. So similar way here also, whether I am taking the integral from 1 to infinity or some number, let us say 3 to infinity, this convergence will not change. So still integration from 3 to infinity also converges if p is greater than 1, right? So from which real number we are starting, that is that will not change the behavior of the integral when the function is nice enough, like a continuous function, right? If there is the function is unbounded, then we have to check. But for this kind of function, when this function is bounded on the interval 1 to infinity, so therefore the convergence behavior will not change. So we have seen other examples also, and this is also important example, that e power minus t dt, this integral is also convergent. So in comparison test, mostly we use these two functions, one upon given function which we want to integrate. We want to check whether it is convergent or divergent. We compare with these two functions, basically 1 upon t power p and 1 e power minus t. So this is comparison test, that whenever we have a given function ft, we can find a function gt which dominates f, and if the integral of g converges, then integral of f converges. And we discussed one example already. So this example I have given. So did you try this example?
Yes, sir.
Yes, sir.
Yes, sir.
So what is the answer?
Convergent.
Convergent.
Converges.
Yes. So how do we conclude that it converges?
Sir, by
Sir, it is
comparing
less than
e to the power minus x.
This function is dominated. So first of all, this function is non-negative, and it is dominated by e power minus x for all the numbers of the given interval. So for 1 less than or equal to x less than infinity, right?
Yes.
So this is our ft function, that is here now variable is x, and this is our gx, and then integral gx converges so by comparison test, integral f also converges. So So this was just a simple example which most of you have already done. So here you can see that we are comparing it not 1 upon t power p, but the other function. And another thing to note here is that this function is not integrable directly. So, but what we are saying is the area is finite. We are not exactly finding the area of the function. We are only saying that area is dominated by area of the function e power minus x. Okay, very good. So now today I want to discuss limit comparison test. So let us see what is the statement of limit comparison test. So we in short we write LCT. So suppose we are given two functions. First function is non-negative, and second function is strictly greater than 0, because we are going to divide by the second function for all values of t greater than equal to some fixed number a. So first condition is that we will find the limit of the quotient. So limit, as we want to see the behavior at infinity, integral ft by gt t goes to infinity, whether this limit is greater than 0, that is first case, or in the second case, if this limit is infinite. So in either of these cases, what we will get is that the integral a to infinity ft dt converges if and only if integral gt dt over the same interval a to infinity converges. Right. So the behavior of the area of f over this infinite interval is convergent, is a finite real number if and only the area of g function is convergent whenever the limit of the quotient is greater than 0 or infinity. So now the second case is when the limit is 0. So if the limit t goes to infinity ft by gt is 0. So in this case, we will get only one way. So if the integral of the denominator function converges, so if limit is 0, then the integral of denominator function converges, implies the integral of the numerator function converges. So this is the statement of the limit comparison test. So sometimes we cannot apply the comparison test.
सर ये दोनों कंडीशन सेम नहीं हो गई?
In the above first part, we consider the limit is greater than 0 or infinity.
No sir, that then part, मतलब if this is true, then this happens, then
this happens. Then the conclusion is that whenever this converges.
सर ऊपर वाले में भी तो यही हो रहा है लगभग.
So if you want, I can rewrite as end here and this.
नहीं वो नहीं बोल रहा सर, इसमें भी तो देखो जैसे gt कन्वर्ज करेगा तो ft कन्वर्ज करेगा, और ऊपर वाले में भी अगर g का इंटीग्रल
वो डबल इंप्लाइज है.
here double implies is there. So
Okay,
double implies means we know that. Uh,
yes,
so
sir. Yes, sir. Got it.
so double implies what we conclude is integral ft diverges, then integral g also diverges in this case. But now here, if integral f diverges, then integral g diverges. But integral g diverges, that doesn't imply integral f diverges, right? Because it is not both the way.
बट सर हम बी में ऐसा बोल सकते हैं ना एफ टी वाला इंटीग्रल डाइवर्ज करता है तो जी टी भी डाइवर्ज करेगा इन द बी केस.
Right. So we'll conclude that from this statement. So contrapositive we can use in B in that way. So that is true. So let us see one example. So is the integral one to infinity 1 minus e power minus x divided by x convergent? So we have to give explanation also. So we'll give explanation also in this case. So let us write down the solution. So the methods we studied so far is either we can directly use the definition of improper integral, that is limit extends to infinity integral 1 to x fx dx, whether it is if the limit exists then it is convergent, otherwise no. The second test we use is comparison test, and the third we studied so far is limit comparison test. So these are the three methods we studied. So so let us try whether we can apply the comparison test directly. So to apply comparison test, we can easily note that this function is dominated by 1 upon x for all x in the interval. All right. So note that this holds, and in fact this is also non-negative. So question is, can we apply the comparison test? So as you know that this integral 1 to infinity 1 upon x dx is divergent, right? Because we already studied that integral 1 upon t power p. So here it is x power p is divergent when p is 1. So this is p equal to 1 case. So this is divergent, and we know that whenever this integral converges, integral of this function converges by the comparison test. Here we have this integral is divergent. So therefore we cannot directly apply. We cannot apply comparison test by taking fx is 1 minus e raised to minus x by x and and gx is 1 upon x, right? So this is in bracket. So this is just explaining, I'm explaining that we cannot directly apply limit comparison test here, but this will give us we cannot apply the comparison test. So we give here hint that we cannot apply comparison, but let us see if we can apply with the same function the limit comparison test. So let us try that whether we can apply LCT by considering g of t or g of x is equal to 1 upon x. So to apply limit comparison test, we know that we have to find the limit of the quotient of f and g. So note that for fx is the given function, that is 1 minus e power minus x by x. The limit of x tends to infinity, fx divided by gx. So that is 1 minus e power minus x, limit x goes to infinity, divided by x, and in the denominator we have function gx, that is 1 upon x. So now we know that either we can multiply x in the numerator or denominator, or by cancelling 1 upon x we get this limit as limit of 1 minus e power minus x. And then we know that e raised to x is increasing function, it approaches to infinity as x tends to infinity. So e raised to minus x approaches to 0 as x tends to infinity. So limit is 1. And the criteria of limit comparison test is limit is greater than 0 in this case. So therefore by uh, by limit comparison test, the integral of f is convergent if the integral of g is convergent. So let us see what is integral of g. The integral gx dx is we have already observed that this integral is integral 1 to infinity 1 upon dx is divergent. And since it is divergent, by applying LCT we get that integral 1 to infinity fx dx which is 1 to infinity 1 minus e power minus x dx is also divergent. So what we are using here is because limit of fx by gx is greater than 0, right? So this is one of the example of limit comparison tests where we can directly not apply the comparison test, but with the same function we are applying the limit comparison test. So let us see some more example. So question is 3 to infinity x dx by x cube plus x power 5. Is this integral convergent? So in this example, the integration is from 3 to infinity. All right. So the interval over which we are integrating the function is 3 to infinity. So it is not necessarily that every time we integrate the function from 1 to infinity. It depends on from which number we are starting. So to find now we need to see that whether this function is integrable or not. So let us start by observing this. So here my function is let us say t. If I change the variable, then it is just t divided by square root of t power 5 plus t power 3. So what I will see is basically I need to find the limit as t goes to infinity of this function divided by some another function gt. So which function we shall compare this particular function, so that I want to find. So to find that, one of the idea we usually use is that we take the maximum power of t, which is common from the numerator and denominator, right? Or sometimes we can also apply the L'Hospital's rule. So let us see if we can find the maximum power of t in the numerator. So that is t itself, and the maximum power of t in the denominator will be square root of t power 5, right? So that is square root of t power 5. We'll take t power 5 common, so it will be 1 upon t square. So now if we cancel the power t from the numerator, what we will get is 1 upon or directly also we can write this as t divided by square root t power 5 1 upon 1 plus 1 by t square. So now we know that if the limit of this bracket will be what as t tends to infinity, what will be the limit?
1.
1.
That will be 1, right? So if I take this as a function gt and then I divide ft by this function, what I will get is the bracket function, and then the function in the bracket has limit 1, so I can apply the limit comparison test. All right, so this is the motivation how we find the gt function for this type of quotient of the polynomial. So this computation gives us the function gt which will take as this function t divided by t power 5 by 2. So if we convert it into the power of t in the denominator, then it will be 3 by 2, right? So here what is p? P is 3 by 2, right? If I write this as a 1 upon t power p, then p is 3 by 2, and 3 by 2 is greater than 1, so this integral converges. So it converges from 1 to infinity, but 3 to infinity also it converges, because then the area in the 1 to 3 interval is anyway is a bounded area of the integral of 1 upon t power p. So now we can write down that. So also we get limit t tends to infinity ft divided by gt, which is nothing but limit t tends to infinity. So when I divide ft by gt, we'll get limit of this function 1 upon square root 1 plus 1 upon t square, and that we already observe it is 1. It is 1. So this quotient limit is greater than 0. So now we can apply LCT, since the integral 3 to infinity 1 upon t power 3 by 3 power 1 upon t power 3 by 2 is convergent, we get the given integral is convergent. So as I said earlier also, you can apply here if you are comfortable with L'Hospital rule, you can also apply that. So let us see one more such example. So any doubts so far? Hello, any doubts so far?
No, sir.
No, sir. No, sir.
Okay. Yes.
तो जब हम किसी इंटीग्रल का बोलते हैं कि वो कन्वर्जेंट है डाइवर्जेंट है, इसका मतलब क्या हुआ कि जब हम उसको मतलब उसका इंटीग्रेशन करके कुछ वैल्यू निकलेगी तो मतलब कुछ निकलेगी उसकी वैल्यू अगर हम उस बोलते हैं कि वो कन्वर्जेंट है वो इंटीग्रल, और हम
Yeah.
बोलते हैं कि वो
So that
डाइवर्जेंट है इंटीग्रल, मतलब
that integral is real number basically. That means it is convergent.
मतलब जो एरिया उसका आ रहा था हमारे फंक्शन का वो एक रियल नंबर है, और डाइवर्जेंट आ रहा है इसका मतलब इन्फिनिट एरिया आ रहा है।
Either the area is infinity or the area we cannot find. So that means the limit extends to infinity. Integral 1 to x fx dx ft dt does not. We cannot find that limit extends to infinity.
ओके सर।
Right. So
Sir,
convergent means area we can find, and that is real number. It may be positive, area may be negative also.
sir means when it will be infinity, the function may not be bounded.
Yes. So if the function is non-negative and we are finding its area, for example, then area will be, since the function is non-negative, area will be positive. So if the function, even the function is bounded, for example, if we take ft equal to 1 itself, then for that function ft equal to 1, constant function 1, if we integrate from 1 to infinity, it is area is infinite even when the function is bounded. So therefore we have to check actually either by this test or by finding actual limit, whether the limit is exist and it is real number or not. So let me take one more example. So the question is that is integral 1 to infinity 1 upon t square plus 1 power p dt is convergent. So here basically we want to find values of p for which the given integral is convergent. So here if we observe this function, so the function depends on p, and it is given in kind of 1 upon t power p. It looks similar to the function 1 upon t power p. So we know that the integral 1 upon t power p when it converges and when it diverges. So what can we do here is we can convert this function in powers of t, and we can compare with that function. So we'll use the same idea which we used in the last example. So here the function is this one. So if we take the power of t, which is common in numerator and denominator, then what we can observe is we will convert this function as if I take t square common, then we'll get t square power p 1 plus 1 upon t square power p. So one of the reason why we are taking the power of t common is we are basically getting a term like 1 upon t square, and then we know that when t goes to infinity, 1 upon t approaches to 0, 1 upon t square also approaches to 0. So which function will take as a gt here?
1 by t to the power 2p.
Right. So if I take this function as a g function, and then we take the quotient, then we'll remaining with this function, and it has the limit 1 as t tends to infinity. Right. So that is basically the idea. So here we will take the function gt to be 1 upon t power 2b. So now uh, the limit of the quotient, let us first check whether what is the limit of the quotient, then we'll see how to apply the limit comparison test. So limit of the quotient is ft divided by gt, and that is limit t tends to infinity. So we know that when we divide the given function uh, ft by this function gt, will remaining with the 1 upon 1 plus 1 upon t square power p, and then as we take limit t tends to infinity, this limit will be 1, and that is a positive number. So what we get finally is that, but therefore by the limit comparison test, the integral 1 to infinity 1 upon t square plus 1 power p converges if and only if the integral 1 upon t power p converges. Right. So now the behavior of this integral depends on the behavior of this integral. So we need to just check that whether this integral, when it converges and when it diverges. So we already know the test function example, that integral 1 upon, yeah, any question? Okay, so we already know one example that when the integral of 1 upon t power 2p dt, when it converges, and when integral of 1 upon t power p when it converges for which values of p and which values of p diverges. So it converges for p greater than 1. So when the power is greater than 1, right? So by the, we can say p integral test, right? That test function result. So p integral test, we know that the integral 1 upon t power 2p dt converges if what will come here?
P is greater than 1 by 2.
Right. So the power is greater
Yes.
than 1. Right. So this is greater than 1, and it diverges when the power is less than equal to 1. So then what you said directly is right, that therefore it converges if so now we can directly take the given integral converges if p is greater than half, and so we have to write dt also, and it diverges if p is less than equal to half. Right, so that is exactly this, p is less than equal to half. So this way we can use the limit comparison test and compare with the with the given. With the known result, we can derive the similar example we can apply there. So let us see one more example that is the integral 1 to infinity sine 1 upon t square diverges. So we need to check that whether this integral converges or it diverges. So what do you say? How will check that?
1 by t square से multiply divide कर देंगे फिर.
1 by t square. So which test we will apply that?
Limit
Which
comparison test.
right. So we'll go for the limit comparison test. So here our given function is 1 sine 1 upon t square. So we'll take the function gt to be 1 upon t square. So if you take this function, then let us see what will be the limit of the quotient. So if we take limit of the quotient, then limit t tends to infinity ft divided by gt is limit t tends to infinity sine 1 upon t square divided by 1 upon t square, and then what we know one formula of the sine function, limit formula. So that is sine x by x. So this limit looks like that, right? So what we shall do here, we will
It is 1.
1. So it tends to 1.
Yes.
right.
1.
It tends to 1, and the exact formula is that limit x tends to 0 sine x by x is 1. So for that we have to first convert the limit into x tends to 0. So for that what we will do, we will substitute one variable. So substitute x equal to 1 upon t, right? If we substitute x equal to 1 by t, we get limit x tends to 0 sine x square divided by x square, right? And then we know this limit is 1. If there is confusion, we can again substitute y equal to x square, right? So we get limit y tends to 0 sine y by y, and that is 1. So finally limit is greater than 0. So the behavior of integral of this function is same as behavior of this, and we know that this integral converges, so therefore given integral converges. So therefore by limit comparison test, integral 1 to infinity sine 1 upon t square dt is convergent, right? So what is the reason? Because 1 upon t square is convergent. So we have to note that here why we can't use 1 upon t as gt. So is it clear we cannot use gt equal to 1 upon t?
Yes, sir.
Yes, sir.
Right? Because if you substitute gt equal to 1 upon t, we'll get here sine x square by x. And then even if we use this substitution, we'll get here sine y by root y. And that is a different formula, not the known formula. So even we cannot find limit there. So therefore, here we are taking 1 upon t square depending on what power given here. So let us see just last example of this type. Integral e power minus t power p dt. So what can we say whether it is convergent or divergent? So any idea about this integral? So what shall we do here?
So इसको तो डायरेक्टली
I think we should do it by part.
We can do integration by parts, that is one way, but is any other way directly? Can we apply some test or
So that e to the power minus t dt from 1 to infinite it converges. So from there we can.
yeah, so we can use that result and compare. So we basically use the comparison test. Yeah. So we know that e raised to minus t power p is certainly it is a non-negative function, and it is less than equal to e power minus t for every t greater than equal to 1. So therefore we are taking from 1 to infinity, because here we can compare these two functions.
सर ऐसा हमेशा नहीं होगा
Pardon?
सर ये जो रिजल्ट लिखा है तो किसी मतलब बड़ा होगा ना e raised to power minus t into t raised to power p क्योंकि t greater than 1 है
सर t की पावर p बड़ा होना चाहिए
Yes, sir.
Yes, sir.
So
Yes.
let us see. So t is greater than equal to 1, so t power p is also greater than equal to 1, right? So that will be bigger actually. You're right. So that it depends on well. Yeah, so this is a non-negative function.
p का वैल्यू स्पेसिफाइड नहीं है.
So can we apply it directly with limit comparison test? Let us see. So if we take gt equal to e power minus t, so what will be the limit of the quotient? That will be limit of the.
सर इसमें लिमिट कंपैरिजन टेस्ट में अगर हम दूसरे वाले को t raised to the power p ले लें तो कंपैरिजन कर सकेंगे क्योंकि वो वाला इससे बड़ा होगा और फिर कन्वर्ज कर जाएगा
Right. So if we take t power p, then limit of t tends to infinity e power minus t is 0. Right. So in that case, we can apply the second part, b part. So what b part says? B part says that B part says that whenever G converges, this converges. So in that case, T power P converges. So if we take here T power P, then we'll get this as E power minus T, and that is 0. So therefore by LCT, the integral of f converges if integral t power p converges. So for which values of p this integral converges?
Greater than 1.
p less than 1.
P less than 1.
Because here we have a t power p in the numerator. This converges if p is
Then 1.
less than 1. Now for other powers of p, we need to check that. So that I have not done, so that I will give as an exercise. So
तो शायद
check
कन्वर्ट नहीं करेगा.
No, we
This is
already proved that it converts this for p less than 1.
t raised to the power
Other,
p से
other we are saying.
1 upon
Yeah.
t raised to the power p होता है वो रिजल्ट में, और p greater than 1, क्योंकि जैसे रूट x फंक्शन है तो वो तो डाइवर्जिंग फंक्शन होता है.
सर लेस
P-
देन 0 होगा.
So check for p greater than equal to 1. Okay, so you try this. We will. I have not tried that, so we can discuss it in the next lecture.